Well, welcome everybody to the first community Zoom of 2024. I hope everybody's having a good new year. My name is David Freyer, and I'll just a quick observatory update. The proposal call, the NRAO GBO proposal call, should go out later today. It might be at any time now. The proposal deadline will be Wednesday, the 31st of January. So not the first of the month. It's actually going to be the last day of the month on a Wednesday in the middle of the week at 5 o'clock Eastern time or 2200 UT. That call will go out later today, and you can see the details. The AAS meeting is coming up, and Green Bank as well as NRAO will have a big presence there. We have an NRAO town hall and Monday evening from 6:30 to 8:30 for those of you who are going to the AAS meeting. We also have a GBT special session Tuesday afternoon from 2 to 3:30, GBT large surveys of the ISM and star formation, as well as an associated poster session also later in that afternoon from 5:30 to 6:30. So if you're going to the AAS, please drop in by the booth and come to our town hall and our special session. So without any additional information, I'll just hand it over to Jay, who will be introducing our speaker, Michael Shull. So take it away, Jay.
Thanks, Dave. Our speaker today is Mike Shull from the University of Colorado and the University of North Carolina, Chapel Hill. He'll be speaking on the high-latitude interstellar medium, dust and gas in the galactic halo. Let me remind everyone that this is being recorded for later viewing and that questions should be submitted through the Q&A button in the lower part of your screen. And now let me turn it over to Mike.
Okay, hello. Let me share the screen. Hopefully this is working. How does that look?
Looks good.
Okay. So this is a collaboration that I started with who was then a postdoc at Caltech, Gina Panopoulou. We were interested in combining forces between far infrared and ultraviolet astronomy to look at the dust to gas ratio at high latitudes. I said in the halo, but it's high latitudes. So why is this important? Well, increasingly, understanding thermal dust emission is very important for cosmology and getting rid of the far infrared foreground and submillimeter foreground that you need to do the microwave background studies. So this is a montage of Planck, and I'll be mostly talking about the bottom tier of panels, the far infrared submillimeter, 353 gigahertz lower left. You can see there's a huge amount of thermal dust emission at high latitude. And that's actually the best place to look for polarized far infrared emission. There's also an awful lot you see contributing at 545 gigahertz and 857, the submillimeter. I personally am interested in galactic halos because there's an awful lot of gas and heavy elements being blown up into the halo. This is a dwarf galaxy, not a big one, the famous M82. On the left, a lovely picture taken by Sophia and the Hawk Plus polarimeter showing that the outflows from the nucleus are probably collimated by magnetic fields. And the right is the famous H alpha picture showing the biconical outflows. Similarly, there's been a lot of work in the ultraviolet by Space Telescope Group, Andy Fox and his collaborators, Jason Tumlinson, on heavy elements, oxygen-6 and other heavy elements out at 50, 100, even 150 kiloparsecs around large spiral galaxies. So clearly that gas and probably dust can get blown up or radiatively elevated into the halo. And then finally, just to show some of the targets that we used in our survey, I'm showing this picture. It's a probably very famous picture to radio astronomers of the 21 centimeter sky at high velocity. So velocities above 90 kilometers a second, plus or minus. And you can see I've highlighted complex C, more on that later. A lot of this gas has been churned up from the disk from probably superbubbles and supernova remnants, but some may be falling in from much farther distances. So this is a survey that Bart Walker et al. And the FUSE team published 20 years ago now. It's been surveyed in ultraviolet lines of Lyman alpha, oxygen 6, silicon 3, molecular hydrogen. So this was the sample that we used in our survey to look at H1 and H2 molecular hydrogen and compare it to the dust. So here's a quick summary of the paper. I thought it was going to be out by now, but APJ promises sometime in January, but you can find it on the archive. We expected to see a decrease in dust content, particularly in the low metallicity gas above the plane. But in addition to metallicity effects, you can lower the grain content by destroying the grains in shocks. Some of the dust probably settles to the disk. Other dust grains are blown out or radiatively elevated into the halo where it can get sputtered. For all those reasons, one does expect to see less dust up there, or in this inverted ratio, the gas to dust ratio, an elevated ratio of N of H to color excess EB minus V. So in the disk plane, this is pretty well measured going back to Copernicus satellite and then FUSE satellite at about 6 times 10 to the 21 column density per magnitude. And the classic paper, Bolin et al. 1978 is from Copernicus. Danforth and I had a paper a couple of years ago with FUSE, and Harvey List and Mary von Guerin had a paper in 2023 that I actually refereed, which got my interest again in checking this out. Harvey pointed out back in 2014 that these ratios of gas to dust were elevated. And then Lenz and others followed up and got the same number of about 8 or 9 times 10 to the 21 at high galactic latitude. We find in our surveys, which included H2 along with the H1, a little bit higher, 9 or 10 in those units. But the reason I got re-interested in this ratio is that the two regions are looked at with different techniques. In the disk, we use ultraviolet absorption, Lyman alpha for H1, and the Lyman and Werner bands of molecular hydrogen. So it's entirely UV for the column densities. At high latitude, it's radio techniques. It's 21 centimeter emission for H1. And then instead of using optical reddening toward these OB stars, it's an indirect inference of EB minus V from the far infrared emission. It's dust modeling. So more on that in a little bit. Okay, so first one slide on what we found with FUSE, redoing the classic Copernicus survey, but with more targets and more distant OB stars. This was 139 OB stars, mostly in the disk plane, out to maybe 4 or 5 kiloparsecs. And we got a number of about 6 times 10 to the 21 with some scatter. List and Guerin, the paper that I was referee on, found a very similar ratio of 6.2 at low latitude. Now, I emphasize again, the gas in this ratio is measured by UV absorption lines of Lyman alpha for hydrogen, and then the H2 lines also in the ultraviolet, far ultraviolet for H2. Okay, so switching now to the high latitudes, here's a survey or 2 images of our targets. We looked at 94 of these high latitude quasars. Left panel in each pair is the northern hemisphere, and the right panel, the right circle, is the southern hemisphere. And what we first looked at was how well did these far infrared measurements measure EB minus V, or infer it. It's an indirect inference. And you can see that Schlafly and Finkbeiner, which we abbreviate SF11, looks quite different than the more recent Planck on the bottom. And I'll be referring to Planck GN or GN ILC. It's a technique called generalized needlet internal linear combination. It's basically a way of taking out the spatial fluctuations of the background, of the cosmic background, so you can get at the thermal emission from the dust. So I'll be calling this Planck GN for short. And so these are maps that if you just look at the colors, which is this color coded with the ratios, they look quite different. And we got into this in a very deep way, and I'm not going to get into it in this talk, but the details are in the paper. We prefer the Planck generalized needlet, and I think the Planck people do too. If you want thermal emission from dust and model that to get the grain content, you want to use the Planck number. Okay, so here's what we found, a similar plot of this ratio, and this is N of H, including both H1 and H2. And you can see there's also a lot of scatter. It's plotted versus color excess. And I want to stress a few points about this. First point is we're reproducing the numbers that List et al. Or Lenz et al. and List and Guerin found. A little bit higher numbers. These horizontal lines are the mean ratios of the distribution. We're finding numbers of 10 or 11, whereas List and Lenz were down in the 8 to 9 ratio. Part of that is due to the molecular hydrogen, but another part is that we use the Planck GN, which gives a little bit higher, often a little bit different color excess in inference. The second point I want to emphasize is that values at color excess less than 0.02, 0.03, even 0.04 are highly uncertain for technical reasons. Again, I'm not going to get into it too much, but the modeling is quite sensitive to measuring the dust temperature and its index. But once you get up above color excess 0.04, 0.08, 0.1, it settles down, and we confirm the elevated ratios. Okay, now we got into the velocity distribution. That was something of my own interest since I've worked on high velocity clouds. Turns out that, as you might expect, the ratios of gas to dust in HVCs are different for two reasons. One, there's less dust there, lower metallicity, and two, whatever dust there was may have been sputtered or shock destroyed. So here's one quasar behind complex C. In this case, you can see the intermediate velocity cloud at about minus 80 kilometers a second, and an HVC at minus 150, complex C. And that in this sight line and in others behind these high velocity clouds, the HVC dominates the H1. Okay, so here in one plot shows the distribution of this ratio. You can see they're not quite Gaussian, but there is considerable spread about the means. On the left, the gray stippling shows the old UV values in the galactic disk, the Bolin et al. And Shull and Danforth with Fuse. And those numbers are down around 6, plus or minus 1. And then the three semi-Gaussians in color, green, orange, and blue, those are different versions from different surveys and different subsets of our data. Okay, so let's see. In blue, it says SFD underscore S11. SFD is Schlegel, Finkbeiner, and Davis, the classic 1998 paper corrected by Schlafly and Finkbeiner. So that's blue. SFD 0.884, the orange, that's recalibrated by a different factor, another technical point. You get something pretty close to the blue. And then finally, GN, the green, that's the Planck generalized needlet. And they're all giving similar numbers with means in the 8-9 ratio, or ratio in 10 to the 21 units. So I think we've confirmed the point that List et al. And Lenz et al. Made a decade ago, that the gas to dust ratio is higher once you get above the plane. But, and this is where I want to spend a little time on uncertainties. The top line gives our main result. The gas to dust ratios toward high latitude quasars are about 50% higher. And this is where the velocity matters. If you just look at low velocity gas, exclude the high velocity clouds and intermediate velocity clouds, you get a number of about 9. If you include all the gas, high velocity, intermediate velocity, low velocity, you get 10.6 times 10 to the 21. So it matters what velocity range you pick. And I've noticed in the literature, I really had to be careful, different surveys quote different velocity ranges. Second point, this is a ratio with a numerator and denominator, so there's errors on both. So we got into looking at the 21 centimeter measurements, and I will come back to this, but at the 5% level, different radio dishes give different column densities. So that's something that Jay Lockman and I have been working on offline, and there's a table in our paper that does a preliminary comparison. The Green Bank 100 meter versus the 140 meter compared to other telescopes around the world. And there can be some differences of up to 30% in a few cases, but on average, it's 4 or 5%. And the Green Bank telescope is lower. I hope it's the right number, but it's on the average lower than the others. The second point on that N of H is that you have to include H2. And you would think at high latitude, maybe H2 can be neglected, and often it can. On average, it's only 2 or 3% addition to the total hydrogen. But in a few sight lines at high latitude, it was 10, 20, even 30%. There's a few sight lines where there's molecular hydrogen. Okay, on the right, the EB minus V in the denominator, that's a far infrared estimator. And the SFD 98 and the Schlafly and Finkbeiner 2011 was based on IRAS 100 micron. And that needs to be looked at carefully, because to get the EB minus V, or the optical depth, you have to do some dust modeling. You have to know the dust temperature, and you have to know its emissivity index. And the bottom left, I show the so-called radiance, the integrated intensity. And so you measure the optical depth at 353 gigahertz, for example. That's what Planck often does. And then you make a model, a gray body model, where the Planckian is modified by an emissivity new to the beta. But there's an anti-correlation that's been found between dust temperature and this index. And over on the right is an equation I derived it in the paper, but it shows that this radiance, the total infrared emission integrated to overall frequency, is very sensitive to beta. Even when you measure beta to 10%, it comes in, and you can make factor of 2 have factor of 2 uncertainties. So that's discussed at length in the paper. I just put up a note of caution for that. Okay, so let me wrap up with some of the overall findings. The details are in the paper. First, on the reddening maps, there's the 2 classic papers going back to Schlegel et al. 98 and Schlafly and Finkbeiner 2011. There was the Planck DL, that's the Drain and Lee model, in 2016, and then there was the Planck GN model in 2016 with the needlets. We prefer the latter, and I think the Planck collaboration does too. On the surveys, the paper that we had been using for H1, the FUSE team certainly used it, by Bart Walker et al. And I'm on that paper along with Blair Savage and many others. That was made quite a while ago based on many different telescopes with many different beam sizes. You would hope that the smaller beams would do a better job, but as Jay points out to me, calibration of the telescope is probably as much a factor as the beam size. But we prefer the ones that are 9 or 10 arc minutes. There's also the H14 pi, which is a mixture of Effelsberg and Parkes. So when we compared, I think it was 36 quasars, sightlines, with the GBT 100 meter, with the GB 140 foot, with a slightly bigger beam, and the H14 pi, also slightly higher beam, we found that the Green Bank telescope gave lower values on average, 4 or 5%. But since that EB minus V is in the denominator, that can add quite a bit of uncertainty. So the error bars on these ratios get large and asymmetric once you get down to quasars at reddening 0.01, 0.02, 0.03, which many of them are at high latitude. So here's a summary of our results. I've said some of these things before. In the sample that we looked at high latitude, this gas to dust ratio is about 50% higher than in the disk plane. We've looked at both H1 and H2, and it matters whether the sight lines have high velocity gas or not, because that's probably contributing to the dust destruction. The good news is Harvey List was correct 10 years ago, and follow up also that got elevated numbers, 8 or 9 times 10 to the 21. On the other hand, shed a tear that I wish there were less uncertainty in this far infrared modeling method. Maybe dust modeling will improve. It's still a moving target. There's new ideas from Drain and Brandon Hensley of astrodust, the old model of separate distributions of graphite and silicates seems to be not incorrect, but inconsistent with the polarization measurements as a function of wavelength. So stay tuned on that. There may be some new work coming there. Something that I would love to have radio experts help me out on, and I think Jay has already helped me, understanding which H1 column densities to use and what are the right error bars on that. And then finally, just something that the Plunk people do. They use the 353 gigahertz as a ratio, dust to gas ratio, compared to H1. I think they do that because thermal dust emission is important there, and they have a better handle on the polarization. But as I said in the previous slide, there's large uncertainties in that, could be up to a factor of 2 because of this anti-correlation between dust temperature and its emissivity. So I think that's the end. Yes, that's the end. And I'd be happy to take questions.
Thanks very much, Mike. Please let me remind everyone to submit questions through the Q&A box on the lower part of your screen. And we already have one. Mike, can you say more about the high tail at low reddening? Is this only in the AGN data or also seen in galactic sight lines?
Yes. These tails are only the AGN. This is the survey of 94 AGN. I've looked at, in our 2021 paper with Danforth, I looked at a number of low reddening O stars. The problem is there aren't as many OB stars in the disk, or even at intermediate latitude, that have low EB minus V. But we didn't see the effect. But that's a small number of statistics.
Mm-hmm. Let me say a word here while we're waiting for more questions about the calibration of 21 centimeter data. I am frankly delighted at the thought that it would come in with a systematic uncertainty of only 5%. Each of those surveys that you used had a complicated calibration strategy that was completely independent of one another. And so I think we should be giving ourselves a pat on the back that we've come so close. Clearly, there's more to be done, and it's a tough problem. Let me just end it with that. It's a tough problem.
Yeah.
Yeah.
I put up an extra slide because I thought someone might ask. You can see that's the average, but I put some red arrows for places where the column densities differed. 3C273, there was quite a difference.
That is the worst of all because you're trying to measure an emission line against a very bright background continuum source.
Yeah.
And so we may never get a good value of that from the radio. Yeah. We have another question that came in. Far IR only measures the silicate and large carbon dust, not the paw dust. Could the paw dust emission be used instead?
I am not an expert on PAHs. I know there are those near-infrared features, 9, 10 micron features that you could use. My impression from listening to talks on it by experts is that they vary quite a bit, because the emission is often, they're small grains. The emission is often stochastic. They're heated and they relax. So I would worry about using pause.
Okay, here's another question. Could you discuss a bit the NH over EB minus V ratio and its uncertainty for higher extinction regions in the disk?
Okay, well, I don't have the paper from the Danforth, Shull and Danforth 2021 in this list, but I think it's similar to these quasars. There's fluctuations of about 17% in that ratio. Actually, maybe I do have, there. This isn't the full one, but this is close. You can see there's plus or minus 1 in that ratio. That's about 17%. And this goes out to color excesses of order 1. There was a separate survey done with Fuse by Ratchford et al. That took that number out to the translucent cloud range. So color excesses of up to 0.3, 3 or 4. And I think it's similar. It's 5.5, I think, the ratio. So well within that swath of uncertainty.
Here's another question. Can measurements from Arecibo or FAST be compared to the GBT data? Theoretically, we expect that H1 clouds could be much smaller than the GBT beam, and this is observed, for example, by Marshall et al. In complex C with a 1.1 arc-minute beam.
Oh, I would love to see that survey. I don't have access to the Arecibo data. Maybe someone would help me on that. And I certainly don't have access to the FAST data. But beam size is almost certainly an issue. When I got into the looking at the IRS diffuse infrared emission at 100 microns and experimented around the sight line, there were small scale structure. So I would expect to see that. The numbers that you'll see in the literature in the Planck data are often averaged over 1 degree, whereas the numbers that Schlegel, Finkbeiner, Davis, or SF11 quote, and this is on the IRAS IPAC website, those are averaging over 5 arc minutes. So I think beam size probably is an important issue to look at further.
Here's another question. Which of these H1 surveys has done the best job of removing stray radiation, which can be the major uncertainty at high latitudes?
I'm going to punt that one to you, Jay. I have no idea. I think probably the Green Bank telescope, but what do you think?
I think that there were 2 efforts, one from Green Bank, and let me say that Marshall data at 1 arc minute includes the GBT data as well to give the short spacing and the longer spatial frequencies. So it's not completely independent. But the HI4Pi, of which I was a member, did a good job in stray radiation. And with the GBT, we have a completely independent estimate. So it wouldn't
I remember
hurt.
reading a paper that you were on, Jay. Was it Brown and you and someone else?
And Bart Walker.
Bart Walker was on it, right. And you did a comparison and found there was kind of a 5 times 10 to the 19th component that was not real.
Yes. That paper, though,
I forget which telescope that was.
as importantly, that paper showed a correlation between the Lyman alpha as derived from AGN absorption and the 21 centimeter emission from Green Bank telescope, and found quite a good agreement.
I looked at the Lyman alpha also.
Yeah.
Unfortunately, the errors on modeling the Lyman alpha wings, the damping wings, are pretty substantial. So the errors on the Lyman alpha were a lot bigger than the claimed errors in the 21 centimeter.
We have time for just a few more questions. You only have 55 AGN sight lines. What is needed to boost that number?
Well, we had 94 total sight lines, and only 55 of them had molecular hydrogen in it. So the subsample that I used here was reduced to 55. What's needed is a far ultraviolet telescope that can get down to the Lyman and Werner bands, which are down around 1,000, 1,100 angstroms, to get the molecular hydrogen. And I think just many more sight lines of high latitude quasars, which can be done. The 94 is not, that's not the end of the world. That's just where I stopped working.
We have time for one final question. Would it be important to include the cold H1 contribution, as some directions have molecular hydrogen, suggesting the cold neutral medium must be present, and therefore H1 emission does not trace full column density?
Right. I assume you're referring to optical depth effects. I did check the optical depths for the standard temperatures of order 80 Kelvin, but you're right. If you had differences, fluctuations in temperature, you could be missing some. Something that I worry about even more is that probably is dust in the H+, the ionized component. So the warm ionized medium could contribute hydrogen and some dust.
That is a very interesting issue, and I'm afraid we have to leave the discussion for today since we're out of time. Thank you, Mike, very much for this interesting and presentation. Let me remind everyone that the presentation will be uploaded to the Green Bank Observatory website in about 24 hours. And please join us 2 weeks from now when our next speaker will be talking on a related topic. This is Michael Bush from UC San Diego, discussing the detection of faint normal 18 centimeter OH emission from CO faint dark molecular gas in M31. We hope that you can join us then. Thank you and goodbye.